thank you for the opportunity to be here in Jülich. When one scientist works in plant science, there's always these places in the world that are kind of the mecca for the plant science, and Jülich is one of them. So it's been always on my to-do list to come here to Jülich, and obviously, as Roland said, when I was in Australia, it was quite far away. But now that I'm in Europe, I'm just say easy to fly, even to find low-cost flights to come here. So I'm sure I'll be here more often, and I hope you guys do the same and come to Spain at some point to the beautiful Cordoba. So today I will talk a little bit about well, pretty much like Roland said, my experience in field phenotyping and how almost like a personal journey from remote sensing to phenomics, and now kind of trying to go back into these origins of applying field phenomics to crop management, and show you some examples of applications that we have been developing over the last few years. And then we will just finish up with some thoughts on how do I see that we can move things forward, and definitely many ways to collaborate. So, so I started getting involved with remote sensing, and very especially high-resolution remote sensing back in 2006, and that was before drones were even drones. So that was when we used to call this thing remote control helicopters or planes and things like that. Obviously, then they become drones, and now, as you can imagine, they're really, really popular. Then in 2010, I think it was, I moved to Australia to work in Cicero, originally for 6 months, and I spent there like 7 years, so it's been like a long 6 months for me. But I really enjoyed that, that time over there, and I have to say that I miss Australia a lot. But now I'm back here in Cordoba. I moved back almost 2 years ago. And during my time in Australia, I had the opportunity to work in in this emerging field of phenomics. So just at that time, just a couple of years ago, the federal government funded this Australian plant phenomics facility, which was a great initiative to put phenomics as a cornerstone tool for providing solutions for the food security, accelerating plant breeding, and you know, a really nice way to put innovation into agriculture. So during that time, I mainly focused on field phenomics and developed some solutions. A lot of them were focused on very kind of proximal sensing, and I'll show you some of these examples as well. So how all this starts, you know, I guess if any of you has done manual measurements in the field, like biomass cuts, measuring static water potential, leaf water potential, even measuring gas exchange, you know that it's not something you want to be doing every day in your life. You need to find a solution to avoid that, especially biomass cuts. And when things scale up, it's okay when you have small little experiments, but when you scale up to the order of thousands of plots in the field, you can imagine the logistics, just the logistics of managing the biomass cuts, the ovens and waiting and all that, it's a nightmare. So, and you can translate that to any other physiological measurements in the field. So, it's a very good way to start, and I say that to everyone. Every time I had to take like students or technicians, one of the first things is to take them to the field and do the hard work, and that kind of sparks in their mind a really nice way to say, okay, I need to do this much better. So that is the fundamental questions that, for me, lies behind phenomics and any other remote sensing for plant physiology. But it's very important to choose the right tool for the job. You know, if you want to measure like biomass on a very limited number of plots, that's okay. But obviously, when you need to go for a much bigger scale, that things change. And so it's very important to think about what is the right tool. What is really what I'm measuring? And what is the best way to accomplish that? So there's many tools, and this is just an example of some of the tools that I've been involved with, of developing myself, from sensor networks to, like I said, remote control helicopters and planes, big helicopters, smaller helicopters, but still big, and ground platforms like phenomobiles. And these will be some of the examples I will be presenting here today. So pretty much, like I said, to choose the right tool for the job, we can find these days like two main approaches. One would be like a mechanistic approach, where we understand how, for example, some biotic or abiotic stress is going to make any changes in our plants. So we go from healthy plants, happy plants, to plants that are facing some difficulties, either because you have you know, like a pathogen, or you have water stress, heat stress. So we know that that causes some physiological changes. And that changes can translate into photosynthetic decline, reduction in transpiration, a reduction in the growth rate of the plants, even morphological changes, changes in the pigments, or even some metabolites will be built up. So for each of these processes, we know that we have tools available in the remote sensing and proximal sensing that can help us to evaluate some of these changes. Like, for example, we're looking at photosynthesis, chlorophyll fluorescence will be your main tool. We're looking at transpiration, infrared thermography is probably the best tool you can use. For growth rate and morphological changes, 3D, RGB, LIDAR, and even some spectral indexes related to these changes are a great solution. Changes in pigments with multispectral and spectral, like metabolite build-ups, where we can find the spectral signature of this chemistry, are the right tools, okay? So really, the key is to identify these processes and find the right tool. We will do manually with a use of tools like gas exchange or any physiological measurements, and we make thousands of these measurements. So at some point, these algorithms can learn what's going on and then develop some rules that mix this data in a black box to give you the solution, okay? And that's pretty much what machine learning is doing these days. So the thing is that you still need thousands of measurements to train. Well, it depends on what you're measuring, but you need in the order of thousands of measurements to train these models. And one issue is that these models sometimes can be quite specific to the samples that you have shown the model, all right? So if you're training a model to detect some changes on wheat, probably you could apply that to barley, but I'm sure you won't be able to apply that to even to maize or even to other species. So you have to be really careful what information you feed your model with, because that's really going to define what's going to be the solution. So that's the problem with these black boxes approaches. And then obviously you can combine them in many different ways. So a very important thing always to keep in mind is that to go from these digital measurements to actual physiological estimates, there's a number of steps that there's no shortcut, right? So obviously everything starts with a camera, a sensor on a platform, aerial, ground, handheld, whatever, you name it. But when we're dealing with the imaging sensors, pretty much the first thing we get are pretty pictures, and that's always something that, okay, you see some changes with your eyes, you transform that into colors, but that doesn't mean that we are going to have physical values until we apply some calibration, some corrections. We make sure that we capture the data in the right format, so we have to get access to the raw format of the images. So there's very specific steps that sometimes, especially when you buy state-of-the-art equipment that's sometimes not really designed for doing that. I'm sure that if any of you have been dealing with cameras, it's okay, you get your camera, but okay, this is not really calibrated to get temperature. You're going to get some digital values, so you need to calibrate that. Or you have issues with atmospheric correction. So all these steps are necessary just to get a pretty picture, but where every pixel in the image is going to represent a physical unit. In the case of temperature, we're going to get Celsius. In the case of hyperspectral imaging, we are going to get either reflectance or radiance, right? So we need to apply these processes. But then there's still some challenges. We need to identify each of our experimental units or trees or whatever. So we need to remove the background effects that sometimes are happening and confounding our signal. Like, for example, if we have plots in a breeding trial, we need to isolate every single plot, remove any effects that we have because, for example, these biomass cuts or non-uniformities. And then eventually that has to be matched to the field layout, to the experimental layout, to the treatments, to the plot, and essentially to the genotypes that we're mapping, and we're trying to estimate these traits, these phenotypes, okay? And that's always something that a lot of people underestimate, especially when doing field phenotyping, because you have a lot of things involved. You need to understand all these geographical systems to be able to get that into a GIS, and sometimes people send in the data in a geospatial system that doesn't fit what you have in the other data sets. So there's a lot of disciplines involved into doing this. So always try not to underestimate this process, because sometimes it can take a lot of time. So I'm just going to show you some examples of applications that we've been dealing with this approach. One of these is the use of aerial thermography. As you can imagine, aerial thermography is something very relevant when we're dealing with water-related traits, mainly because transpiration has a direct effect on canopy temperature. So this is our drone that we use in CSIC, mainly because we couldn't use a main area vehicle, so we just went for a full-size helicopter. The other reason is where we're flying quite large areas, which means that could be hardly covered by any UAV. And then the beauty of this is that we could mount a full-size infrared flare camera that was calibrated, will already give us like actual temperature, and we could mount other cameras as well. And the beauty of this is that we could cover like a few thousand plots in just 10 seconds to do this flight. And then we had a few of these experiments in the same location, as you can see here. So we used to take this helicopter to fly every hour on key phenological stages. The interest of this is that when people has been using canopy temperature as a trait for this, trying to improve transpiration efficiency, the experience that people found when measuring manually with the infrared thermometer is that it was a very noisy measurement. It was people were getting heritabilities of 0.1, pretty much noise. When you cover this thing in a few seconds and you remove any of the environmental effects, we started getting heritabilities of 0.6 or even more, depending on the experiment. So people now realize the value of this, and now there are a lot going on in CSIC, developing QTLs and even dynamic QTLs that we can see at different times of the day and different phenological stages. So definitely a very interesting tool. A lot of people think that using a full-size helicopter is going to be expensive, but the matter of fact is that when you are flying like 10,000 plots several times in a day, and you calculate the price per plot, it's not too much when you compare that with the manual measurements and the value of the measurements, which is the key thing. So, like I said, the beauty of this is that we can cover this variability, this spatial variability. Applying this methodology, we can select every single genotype and the treatments, and then we can start looking at the dynamics of these genotypes. And then we see very interesting stuff, like you can see in this image. There's some areas that were cooler earlier in the day, 8 o'clock in the morning, and this was in fact that there was some big trees over here that they were casting such shadows on these plots. So again, how do you interpret that information if you're just measuring at that time of the day, or you know that these plots are going to get less light than the plots nearby? That spatial information is very relevant, and how the biometrician can interpret that data in the statistical models is just amazing. But sometimes you don't need like a very fancy equipment. Even like a single high-resolution color camera can be very, very useful to create some of these amazing data sets where by merging the data and making stereo reconstructions out of these images, we can get very good estimates of the canopy height, but also some information about the canopy density. I have to admit that I was blowing up when I saw this data set, and the quality of the point clouds that we can get from these high-resolution images as almost like what we can get from the LIDAR that I will show in a minute. So you can see the biomass cuts, you can see the differences in architecture, some more erect, some less erect genotypes. You can even see the relief of the terrain, and that's just using a color camera, a DSLR camera mounted in a helicopter, but with high density ground control points. You can see the vertical structures on the ground. So again, the tools really depends on what you're looking for. If you want to measure canopy height on a large scale, then you can use just a digital camera and make 3D reconstructions. But sometimes the resolution we get from the air is not good enough. We need to get much closer to the crop to be able to see things with higher details, or to even to use some instruments that will be very hard to mount or to interpret when we're flying up in the sky. This is an example of some of these phenomobiles. These are, I guess most of you are familiar with ground platforms, like big platforms, like the big LEMNATEC field analyzer, which are fixing allocation. Well, our approach has been quite different. What we've been trying to do is make platforms that can go to the experiment. Rather than to put the experiment in our platform, we already have a lot of experiments. We just want to take our tools and scan the experiment with these tools, and that's pretty much what phenomobiles are. So this was the first phenomobile that we developed, and the matter of fact was that it became really fat. It became so heavy that we couldn't transport it to the experiments, and the first time we go to take this to the experiment, we had to hire a big truck to take it to the field. Then the wheelbase wasn't adjustable, which means that we could then scan on different experiments of different people using different sewing machines. And just the logistics of moving this thing around the computer, everything was too complicated. So that's why we decided to put this phenomobile on a diet and make this smaller phenomobile, which we call Phenomobile Lite. As you can see, it's a very simple structure where we can mount our sensors with an electric wheel from an electric bike, and then you can push it around. And the main thing, the main instrument that we have here is this LIDAR. And I'll talk a bit more about that in a minute. But you can see it can operate inside a glass house, outside, and just manually operate it. So the kind of information we can get from this one is canopy height, fractional ground cover, digital estimation of biomass. We can also mount all the sensors like a green seeker for NDVI, high resolution camera. So it also allows to mount other more complicated cameras like hyperspectral line scanners, or even a thermal camera that can give us much higher detail about even what's the temperature of single organs in the plants. Or with the hyperspectral, we can map every, like I said, every pixel. We can get the reflectance and get down to the chemistry or chlorophyll fluorescence. So like I said, the main instrument for me in this platform was the LIDAR. For those who may not be familiar with LIDAR, LIDAR stands for light detection and ranging. And pretty much what LIDAR does, it will give us a 3D reconstruction of the canopy. But because it's an active sensor, it has a laser, the laser penetrates into the canopy and then gives us some details about what's going on inside the canopy. Compared with the data that we can get from a 3D reconstruction from the airplane, the difference with this is this penetration that allows us to see what's going on and the distribution of the biomass inside the canopy. So the LIDAR operates in a very simple way. It's just a mirror that scans over time, this laser beam, and we just get a measurement of the distance, the angle, and the intensity of that return. And in this case, the color of the laser is very important because in our case, we have a red laser. As you know, chlorophyll absorbs most of the red light. So by measuring the reflectance in the red, we can get an estimation. In this laser, it's not very good, which means it's not very quantitative measurement, but at least it will get us an information about where the canopy is still green or it's not green. If we had a much higher resolution, then we could even somehow quantify the chlorophyll concentration in every spot that the laser hits. And there's many things that influence on the laser, like the speed and the angular resolution, the distance resolution, but I won't get into that right now. So pretty much the way we interpret the laser is there's two different ways. One would be like make a 3D reconstruction of your plants and then measure everything you're seeing in the plants. But we go for a kind of a more statistical approach. What we do is we take all the returns for a single plot, and then we analyze that distribution of those returns. So this gives us this shape that gives us information about the probability of the returns on each of the layers that the LIDAR has scanned. As you can see, we get like a quite strong return from the ground, and then different returns for the plot that give us an information about that plot density. So if we subtract the height from the ground and the top of the canopy, then we get a very accurate way to estimate plot height. And that's something that is very simple and can be done very quick. So the only thing is that we need to decide what is the optimal for selecting the top and the down of the canopy. But then when we compare that with the manual measurements, we get this beautiful correlation where we can really see that the LIDAR provides a much more accurate measurement of height than even manual measurements, just because you have the human factor, just looking where do I put the top of my canopy at this point. But because it's a very fast measurement, it means that people can go there every week and start getting some growth rates for canopy height, for example, that then you can start interpreting in a more dynamic way than just a single measurement. The other thing we can do once we have the LIDAR is we can convert that point cloud into an image that then we can use to extract ground cover. Ground cover is a very important estimate of light absorption, but also the problem is that normally these things are done with a digital camera, just taking a photo of the plots. But the problem is that as the plot grows up, then you start having a lot of shadows inside. And also that is based on green, no green pixels, so it means that when you start getting into senescence, then that algorithm doesn't work very well. Well, with the LIDAR we can say, okay, anything above like 5 centimeters of the ground is going to be plants, anything below are going to be ground. And then we can estimate this way ground cover, even no matter what the color is, just based on the height of the plot. But we can use the red, non-red reflection as well, which means that, again, it doesn't rely on any light conditions. We just measure the threshold, and then we can get this canopy and non-canopy distribution to get the ground cover. But probably the most interesting one is the estimation of the biomass. We can do this with 2 different approaches. One is using voxels. So a voxel is a 3D representation of the pixel, if you like, from the LIDAR. So anywhere in our box defining the plot where we have plants, that it means that it's a voxel with vegetation. So we can somehow interpret that information into a digital estimation of volume that gives us an indirect measurement of biomass. And when we apply this at different stages, each of these colors represents a different step in the phenology of wheat, we get this relationship between the estimated biomass from the LIDAR and the measured biomass from the manual measurements. So the interesting thing is that when we compare that digital estimated biomass with the manual measurements, the heritabilities that our colleagues are getting in the experiments are even higher than the destructive measurements. And the reason for that is that, well, first you have all these instrumental errors that you have when dealing with biomass cuts, but then also this digital image integrates the whole plot when estimating the biomass. While when you do a biomass cut, normally you only take a small fraction of your plot. So that increased information provides more information when estimating the biomass that therefore gives you a higher repeatability. But the main thing is that, like I said before, when you do this manually, just to give you an example, some of the trials that we had there in CSIC, they had like 10 people doing biomass cuts for one day, for the whole day, just to do the cuts. One single person takes about 2 hours to do the same thing, just working with this phenomenon. And the data processing is pretty much trivial. So obviously this means that 2 things is that you can cover much bigger experiments at a lower cost, but also that because it's a non-destructive measurement, you can go time over time and start looking at biomass accumulation without having to destroy your plots. So that's really one of the things to keep in the back of our mind where phenomics can really make a change. It's a non-destructive way to do this estimation. But then we can analyze the LIDAR in many different ways. One possibility is looking into this capacity of the red laser to distinguish between the red, the photosynthetic and non-photosynthetic vegetation. This is an animation that shows 2 genotypes with 2 very different architectures. These are 2 near-isogenic lines for the presence and absence of ligules. And that is what gives us this very erect canopy. And then we can see how, over time, the 2 genotypes maintain, and we have 2 treatments here. We have irrigated and rainfall. And we can see how the genotype maintains the architecture So this is kind of a cross-cut profile of the plot. And we can see how they maintain the architecture, but also how this allows more light penetration. And what we actually see here is that these select lines are able to maintain for longer this stay green trait, because light penetrates into the canopy, while in the one with the legules, then the light doesn't penetrate much into the canopy, and then actually we see less photosynthetic active tissue there in that part of the canopy. So it's something that would be really, well, not difficult, but very time consuming to evaluate manually just by measuring chlorophyll or estimating even like greenness visually. It takes a lot of time just to process this information. And then we can see again this over time and look at the dynamics of these canopies and how all these canopies are changing over time. So this would be for a single genotype, and this would be on a single point in time for many genotypes. And you can see how the LIDAR is picking up these differences in the distribution of the leaf area index at the different profiles, which we're trying now to convert into light interception, to just looking into radiation use efficiency traits that we can then try to analyze and start looking into QTLs and all the genomic stuff that goes behind. But we've been trying to expand to other crops, not just wheat. So just before I came back to Spain, we developed this Phenotyping for grapes. We call it Grover. It's pretty much the same concept. So a lightweight aluminum structure with a LIDAR mounted on an angle. So instead of scanning from the top down, it scans from an angle. And then we get this nice 3D reconstruction of the grapevines that we've been using to analyze things like leaf area index, light penetration, biomass for pruning. Again, trying to do this in some of the breeding programs that they have for grapes, but also to look at other things, more into the management and precision agriculture thing. But like I said, we're putting a lot of effort into this dynamic phenotyping. How do we better characterize these interactions between the genotypes and the environment? And for that, you really need to have somehow continuous, or at least high frequency measurements of your genotype and the different environments. So then we can start looking at how this genotype is going to react against these changes in the environment, or even changes in the management. So one of the best solutions I found so far is the use of sensor networks. So we've been developing different sensor networks for canopy temperature, like this one. Another very important aspect in the whole phenomics thing is really making good measurements of the environment. And one of the things we're doing recently is to develop like a low-cost weather stations of sensing solutions for measuring and characterizing this environment, even using, like we're doing right now, 3D printing for creating these low-cost environmental sensors that allow us to have a really dense and high-quality characterization of the environment. So this is an example of canopy temperature where, by continuously measuring temperature over time, where we go from a period of relative low temperature, maximums of 20s, even some frost, in just a few days we go to 35 degrees canopy temperature, so close to 40 degrees ambient temperature. And what we can see here is like how these three different genotypes, each of these colors represent one genotype, they evolve in different ways. We have one, this red genotype, which has been selected for a low canopy temperature with normal infrared thermometry. The green genotype is a genotype selected by carbon isotope discrimination, so has a higher stomatal closure, if you like. So as you expect, it has a higher temperature. And then we have the blue one, which is a commercial genotype. And you can see how the red genotype is able to maintain this higher canopy conductance compared with the other ones, while the blue is kind of struggling and eventually getting to the same temperature as the green one. And the green one just maintains low conductance, low stomatal conductance, because it's the way it was selected. So again, it really depends what you're targeting. What is the ambient that you're targeting? And you're looking for more conservative plants that conserve more water over time, then probably you're looking into this kind of trait, where if you're looking into yield potential, you're probably looking into a higher conductance to increase photosynthesis. So organizing the data in different ways, we can take, for example, canopy temperature, and then by looking at these colors, we can clearly see what are the cooler genotypes and the warmer genotypes, which would be the blue will be cooler, which means higher conductance. The red will be more conservative. And we can apply this to, I won't go into too many details, but these are like isogenic lines with the different plus-minus traits. And then we can start looking at this behavior. But the very interesting thing is that if we aggregate the data by time of day, what we can see is how all these different genotypes, they have different patterns of conductance over the course of the day. And we see how there's even a few hours shift in the time where they do the maximum conductance, where they have the stomata more open. And that's something that we can only pick it up because we have this highly detailed information continuously. So if we couple this with the environmental conditions, then we can see how, well, are these changes really reacting to changes in the VPV, in the radiation, and so on. And that's what we're trying to do right now. So let me tell you a story about the usefulness of using canopy temperature and what we're trying to attempt now, which is, okay, let's really integrate this interaction between the genotypes and the environment, but also the management, and how we can use the management as well as a way to force some of these interactions and the expression of these traits. So this is a flight that we did in 2009 in California. This is one of the biggest almond orchards in the world. We had the opportunity to do an experiment with the University of California, Davis, where you can see these gradients of colors. Blue means cooler and yellow means warmer. So these are 10 different irrigation treatments, from 100% evapotranspiration to no irrigation. So you can guess that the ones that got more water were cooler, they were transpiring more than the ones that were getting less water. And we had two varieties of almonds, two main varieties that they used there. And as you can see, this is an aerial image from a drone with 40 centimeters spatial resolution. So after applying this methodology, one more thing. Keep an eye on this tree here, right? You see this purple tree that somehow it's a color that shouldn't be in that row because it's more like a yellow-orange kind of thing. So I pick up this tree. So we applied our segmentation algorithms to extract the temperature of every single tree, relate that with the treatments and so on. And here is again this tree, this yellow tree that should be orange according to this treatment. So what happened there is that we found this tree, we were there, just flew the drone, well, the airplane, went to the farm manager, was having a look to that, pick up this tree, and I said to the manager, okay, there's something wrong in this tree. This tree shouldn't be that cool. It should be a little bit warmer. There's something wrong with the irrigation system or something. So the guy was scratching his head. Yeah, that's impossible. What's going on? So we said, okay, let's count the trees there. Okay, this row and column. Took the car, went there to find that tree. And eventually we found the tree, and we found that the irrigation, the dripper has popped out, and it was getting too much water. And we could even see the runoff of the water. And then the guy was really surprised and said, okay, this gives you an idea about the accuracy that you can get with this technology, and how you can apply that for management. So in our case, what we're trying to do is take this canopy temperature to the next level, and applying physical models to go from temperature to the actual physiology, to the stomatal conductance, canopy conductance. So combining meteorological data with data from the canopy structure that we can get from LIDAR, 3D flights, and everything that I have shown you before, we can combine this data into an energy balance approach and get transpiration or get conductance, and then go to this physiological measurement out in the field, in situ, not just controlled environment, breeding trials. And I think this is very important for these perennial crops. So then, and this was part of my PhD thesis, we can validate that information with manual measurements and get quite good estimates of this stomata conductance from the aerial or from the sensor networks that then will allow us to map this, especially when we have different varieties, but also we're going to have differences in the environment, just because the natural differences that happen out in the field, but also because we can impose some treatments like irrigation treatments and things like that. And then we can combine that information either from the spatial information or from sensor networks, similar to what we showed you before. And then we can start looking at, okay, all these different genotypes with all the differences in the environment, how they're reacting, how they're adapting, and then just use this natural variation at the farm level to be able to retrieve this information and to do this phenotyping in situ that will be quite important for this species where, as you can imagine, you know, with annual crops, the breeding targets are going, okay, say we're targeting like climate change, we're targeting heat stress, drought stress. It's kind of easy for farmers to make selection for the varieties that they're going to have in the fields, but for these crops, they don't have the opportunity or the luxury to say, okay, I mean, let's change my variety of almonds or olives or whatever. Some of these plantations, they are, I mean, where I come from, there are olive tree plantations that are probably like 300 or 400 years old, and they're still sitting there. And these guys are, you know, they suddenly find 400 ppm CO2. We don't really know how they're going to evolve. We don't really know how they're going, all these varieties are going to adapt. So what we're trying to do is apply all this remote sensing to map this variation. You know, we can apply that to any physical trait. In this case, this is chlorophyll fluorescence. This is leaf area index and chlorophyll concentration. And this is, for example, this would be a good example where we have the kind of an orchard. This is the world collection of olive varieties in the world that is sitting in Cordoba. And we can fly this and map these differences in leaf area index or chlorophyll or fluorescence or whatever, and see how that is changing over time. And we can map that over time and track how they adapt to these changes of heat waves or changes of very high VPD conditions by combining all these technologies. So what are some of the lessons that I've learned over my years of experience working with all these remote sensing and phenomics things? Well, first is that phenomics goes well beyond plant breeding. For me, phenomics is high throughput physiological measurements. It's not really, the target is not just for breeding, or I mean, for me, it's a natural evolution of remote sensing in plants. It's how we really integrate the plants in the context of the environment, in the context of the genetic makeup, and how we can measure these interactions. And for me, that's the beauty of phenomics right now. I think it's very important to consider these dynamic traits, these plant and environment interactions that we can only capture with these high temporal resolution measurements. And I think that's a very important alternative to single point in time, because when you measure complex traits like yield is going to be very difficult to predict yield with just one single measurement. But if you integrate many measurements over the growth cycle of your crop, you're going to get a much better information about what's going on and what defines that complex trait. Definitely never underestimate the data processing side. That's really what's killing a lot of projects. That's really something that you give for granted that when you buy some equipment, it's going to come with a processing pipeline, as is hardly the case. One very important thing when people try to go for low cost is really not to confuse low cost with low quality. I think I like a lot better to say cost effective. So take the example I gave from the big helicopter. It's not low cost in a way that, I mean, you get a very big invoice at the end of every flight. But when you take the cost per plot and the quality of the data, that's really what gives you the value of what you're getting. Definitely, there's no universal tool. You need to choose the right tool for the right job, and that's something that I guess many of you know already. And a big challenge that we have right now is that there's still a big disconnect between different communities, like remote sensing, plant physiology, breeding, agronomy, still like scratching their heads about how they're going to use these tools and this information. And I think field phenomics could be a really good bridge to get these communities in touch, and I can see that happening in many institutions right now. Finally, like I presented before, I think there are great challenges, but also opportunities for these perennial crops and how they're going to face climate change and how we can develop new innovative ways to do phenomics in a way that hasn't been really done before, as far as I know, which is like to take this natural variation and this already existing occurrence of different varieties out in the field, and to get some information in situ about what's going on and how these plants and these genotypes are reacting to the environment, that then we can integrate into our more traditional pipeline for breeding and genomics and so on. So yeah, that's pretty much all from me. Thank you and gracias.